And chapter 9 is all about adding things to alkenes. And what we started doing on Monday, because today's Wednesday, is this idea of hydration, this idea of adding a molecule of water to an alkene to give an alcohol. And you will see different outcomes. You will see different regiochemistry based on the stability of carbocations or based on the stability of some transition state along the way. There is a lot to come in this chapter. I reckon I'll be through this maybe next Monday, maybe next Wednesday, but it is a seriously big chapter. What we did on Monday was talk about adding acid, and in recitation we sort of filled this out by saying H3O plus is basically sulfuric acid dissolved in water. We're not using HCl or HBr here because they would give you the HX outcomes. They would give you addition of HBr. We need something here that's non-nucleophilic, and the idea is the sulfuric acid is not nucleophilic, and the sulfate anion is not nucleophilic. So what we'll do here is a protonation step. We talked about Markovnikov selectivity, where you prefer to get the more stable carbocation, and then that carbocation gets attacked by the nucleophilic water, and we end up with this thing, right, in decent yield. So that's this sort of addition of H2O using acid. And it's very good in terms of a procedure. We'll have to deal with some different procedures later because maybe we want the other isomer. But right now, if you want the more substituted alcohol, in this case the tertiary alcohol, you simply add H3O plus to the alkene and you get that outcome. Well, we talked about rates of reaction. This should make some sense. If it really is a carbocation-driven process, then we ought to be looking for tertiary being better than secondary being better than primary, and that's proven by these experiments where you put them next to each other. And how much better is a tertiary carbocation than a primary carbocation? A lot. And there's some numbers that prove that to you. We talked about the mechanism for this. It's picking up a proton in the first step. You've got to be very careful here. The arrows are all the same four types that you've seen before. Yes, you will see some rearrangements because they are carbocations, but it should be starting to sink in now. And looking at the mechanism on the quiz there, it certainly is for most people, at least those who come to class. We'll talk about the deprotonation step at the end being fast, but we've got to remember here that rate determining step in this is the carbocation being formed. Yes, it's a proton transfer, but think about where you're going. You're going to a carbocation, therefore it should be the rate determining step. In this example at the bottom, you can see here you've got an sp2 carbon on the left, which is, what are the bond angles for sp2? What was the shape of sp2? Trigonal planar. So what should the bond angles be approximately? 120, right? So there's 120 in a cycle which is very strained. That's a pretty reactive molecule because it is so strained. If you add H plus and then you add H2O, you'll make this guy. What's this hybridization pattern right there? sp3, what are the bond angles? 109. So is that more strained or less strained? It should be less strained because you've gone away from, you're getting closer to sort of where you can deal with a four-membered ring. So again, it's Markovnikov selectivity. You're adding this in such a way that you get the tertiary outcome. And again, it's not because that molecule is more stable, it's because the intermediate that got you there is more stable. So this idea of being able to set up these experiments to your advantage and how to make it work in the direction you want it to go to is something fundamental and something that you need to have for the second term as we start to design our own experiments and start to make our own molecules. We've seen already that last chapter, I should say, if you take an alcohol and you treat it with sulfuric acid, you get the alkene. It is the elimination process. It was an E1 process. And now what we're saying is that you can start with the alkene and go in the other direction. You might think, well, why on earth do that? And the answer again is because it depends upon what you've got. What can the chemical engineers give you in bulk in terms of the materials we deal with, the raw chemicals we deal with? Sometimes it's the alkene, sometimes it's the alcohol. And if you want the other one, you have to deal with the chemistry as you go. So this idea of dilute sulfuric acid is going to give us the alcohol, is going to be important, and concentrated sulfuric acid gives us the alkene is important. Because if you think about what really that means, dilute versus concentrated, it's the amount of water present. And if I'm going from this material here over there, I need water as a reagent. So I want to have as much as possible, so that when I make my carbocation, the water can come in, trap that thing, and I make the alcohol. In the other direction over here, if we start out with the alcohol, this is a byproduct. We want to get rid of it. So the less of it, the easier it is, right? So it's a matter of concentration. If you have more dilute, you're going to get the alcohol. If you have a concentrated system, you're going to get the alkene. Experiments in lab, what are we doing this week? You're doing the SN2, right? Yeah. Now what's next week? Is the E1. Keep an eye on this stuff for next week. This will make sense when you do the homework and the questions for the lab report. All about concentrated acids. Next week, be very careful. It's all about concentrated acids. So, for example, here we'll think about the conditions you're looking for. You're looking for sulfuric acid. I sometimes write aqueous, but I hope by now, after 3 or 4 years of chemistry, you recognize that sulfuric acid is dissolved up in water. So, therefore, it's an aqueous solution. So, you've got water in there to act as a catalyst, if you like. So, if we start out from last chapter and we drew those starting materials and think about where they go, we'll get that molecule. Absolutely, that's what happened in chapter 8. And the way we made this work is by distilling away the alkene. It should be lower boiling point, so therefore it'll distill off, and we should be able to isolate that in high yield. And that drives the equilibrium to the product. Now what we're saying is that we're going in the other direction. So last chapter we did this, we protonated here, we made a good leaving group, we broke this thing off, we made a carbocation, and that's where we went. Well, what we're doing now in chapter 9 is exactly the opposite. You are starting on the right hand side, you're starting with the alkene and water and acid, and you're going in the opposite direction. So where that mechanism was operating in the past, I can quickly go and say now we're now in this direction. We're starting off with the alkene, and I want you to put these two things together. Why learn them twice? One is exactly the opposite of the other. Make a note of that. Put these two together on a piece of paper, you'll see they're exactly the opposite. So if you know it in one direction, you know it in the other direction, or you should. If we start off with the alkene, what's the first event here? The last event in the previous reaction in the other direction was taking off a proton. So what should the opposite be? Putting on a proton. Because in any equilibrium, if it is a true equilibrium, the forward direction must be exactly the opposite of the reverse direction. Yeah? The steps in the forward direction must be exactly the opposite of coming back. So yes, we'll pick up a proton, as we see over here on the right. We'll make the carbocation, and then we'll have the water attack as a nucleophile, and we'll end up with an alcohol. You can control this by the conditions you use. So if you can take for granted, or if you can understand that this is an equilibrium, and if you just let it go, you'll get some of both, you'll start to think about how to do it in the lab, how to control this thing. If you want the alkene, you distill it away at higher temperatures, and if you want the alcohol, you run it at lower temperatures with an excess of water, and that's how we make this go. So the mechanism there is no more tricky than what we've done, but it does lead to this. This is our first example of a true sort of complex equilibrium in which there are lots of things happening. So I'm going backwards and forwards. I'm going backwards and forwards from the carbocations to the OH groups, to the alkene, to the alcohol, and you have to be on top of how you can control this, how you can make this work, all right? So now we can start thinking about when to put these arrows in, and that's something we do between now and the end of term. You need to make decisions. You can memorize them if you like, but that's kind of painful, or you can understand the underlying principles as to why it should be reversible, and then it's pretty straightforward. Then you can take it into biochem, and it becomes much more fun. So thinking about this, H+ transfer, if you look at the acid we're using, it's a strong acid. If you had to give me a rough pKa for this guy at the bottom left, what would it be? Not 16, it's positive. Negative 1.7, right? So it is pretty acidic. So if that's acidic, you can give back a proton to the solvent, and we can go backwards to the starter material. Good leaving group, yes, absolutely, comes off to a carbocation. And something I'm going to ask you again and again as we work our way through the chapters. Where is the molecule of water after it broke off? It's right there. You think about transition states with the dashed lines. As soon as it's not a bond, it's still there. And it has little lone pairs, and this carbocation needs lone pairs. So we can get that reverse process quite easily in a nucleophilic attack to go back to that stuff. And then the last step, fast or slow for a proton transfer? Should be fast. And of course, that will be reversible because now we're saying alkenes react with acid, and we can go back to a carbocation. So please, next couple of days, put them together, see that they're opposite of each other, and be comfortable with that. Any comments? It's getting good now. All right. So there's the argument about how much acid you want to use. There's the argument about the temperature you want to run this stuff at. Be ready for questions coming up about things like entropy. In one direction, entropy is favored, in the other direction, it's not. So we're going to try and combine all this stuff so that as we work our way towards the end of the term, you put it all together. And at the end of the first semester, the target is to be comfortable with this material so we can get into the second term, which is a lot more demanding. Okay, here we go. We do have to worry about stereochemistry again. We're dealing with alkenes. Alkenes are flat. If you add things to them, you go to something that's three-dimensional. In this system, we can see now something called a prochiral alkene. Everything that you will see that will be termed prochiral is flat. We saw carbocations could be prochiral, right? Once you add that fourth thing onto the carbocation, you can make chiral centers. You can do the same thing with an alkene. So it's not going to happen with every single alkene. You're not going to get chiral products in every single instance because you might be adding a second same group. In this instance, I have three different groups attached. It looks like a propyl over here, looks like a methyl and an ethyl. If I add H2O and I get my alcohols, I'm going to get a racemic mixture. So what's alpha D for this process? 0 if you just take it as the mixture. And that's, again, an important stereochemical clue as we head to the rest of the material in 8. Look at the alpha D. What does it tell you? It will tell you something about mechanism. It will tell you something about how things happen. So there's the argument again. If you're okay with carbocations being flat, tertiary carbocations being the best of, better than the others, we can now add a fourth valence, a hydroxyl group. It's not all there, is it? What's missing from this step? It's actually, this is abbreviated. If I add water here, what's the actual intermediate species here? What needs to happen? There's an extra step needs to happen to get to that final product. You need to deprotonate this thing with the solvent to get there. But ultimately, it gives you 50-50 mixture of these two, all based on similar principles to the SN1 reaction. In fact, it pretty much is an SN1 reaction when you get to the carbocation. Okay? Right, moving along. How many products do we expect for this type of system? I think 2 regioisomers, one in which the OH group goes to tertiary and one in which the OH group goes to secondary. But look at the secondary carbon. How many possibilities there? What would those possibilities be? If I add an OH group to this carbon here, and I've already got 3 different things attached, and I add a 4th, what am I going to generate? A chiral center. A chiral center. So you're going to expect to see the plus-minus idea again. Yes, there'll be the minor products because of the idea of Markovnikov. You want to go through the most stabilized carbocation, which in this case is tertiary, but then on the second molecule, if you make that secondary carbocation and it gets trapped, it can attack from top or bottom, and you get the racemic mixture of those 2 products. So if you simply had a mixture of all of this stuff, and you couldn't separate them, or you hadn't separated them, and you took the alpha D, what would it be? Anybody? Who says 0? I like 0. What's the alpha D of this stuff? 0. It's achiral. And the alpha D of this mixture? 0. Right? So they're going to make you think. Yes? We're not going to sort of memorize stuff and then puke it out in a test. You are going to have to think on this 3rd exam. It really is a test. So this one down here, same question really. Add the sulfuric acid, add H+, add H2O, and again, how many different regioisomers do we expect? 2. One add to the tertiary, one add to the secondary. When you add to the secondary, should we see some chiral centers? Yes, because there are 3 things attached here. The criterion we're using here, that is different to this, is different to the hydrogen attached. You add an OH group, that's a 4th different thing. That's a chiral center, so you expect to see that. Go ahead. Squiggle, yes. Squiggle is a shorthand way, and you will need shorthands in the future, like R groups, because things get very busy on exams. That squiggle is meant to represent 50% wedge and 50% dash. So it's traditional to use it as a racemic mixture. And the little plus minus in the brackets right there, that's telling you that this is a mixture of the positive isomer and the negative isomer, which is the direction of rotation in the polarimeter. How many possible isomers here? 2. One at the tertiary system, one at the secondary system. If you add to the secondary carbon, do I get a racemic mixture or not? Yes, because I have this on this carbon. Up here is different to down here is different to the hydrogen attached, and I'm adding a 4th piece. So I should get the same sort of outcome. What we've done so far, thinking about cataloging chapter 8, and again, chapter 9, this is something we can do in office hours in 10 minutes. If you're getting lost a little bit, if you want to catch up and you want to consolidate, come and talk, and we can write this down on paper. Where are we? Point out some of the commonalities and just send you on your way. It isn't that difficult if you're organized. In these types of reactions, what we've done so far, we've added HX, HBr, HCl in a Markovnikov sense. We then switched things and said in some cases you don't want the Markovnikov product, you want what we call the anti-Markovnikov product, and we had a method for doing that by changing the mechanism. We added HBr and we added peroxides, and for some reason that will become apparent later, that changes the outcome. And we're starting to play this game now of, I want that product, how do I make it? It's a totally different thing to what you've been asked to do before. You will be asked to make a certain product, and you've then got to design the synthesis and come up with how that works, knowing all these reagents. So we did the addition of H2O. This is the addition of H2O using carbocation chemistry, and there's a problem with carbocations. What do they tend to do? Rearrange. So chemists will come up with methods to sort of prove or solve those problems. If those carbocations rearrange, and I want my Markovnikov product, how do I stop carbocations rearranging? You can try yelling at them. It doesn't work, we've tried. But you can then develop different chemistry, different reagents to do so. And this is where this guy comes in. Oxymercuration, demercuration. It's pretty much one of the few uses of mercury in the organic lab that's still used these days. What's the problem with mercury? Toxic. It will kill you dead. Yeah? And anybody read? Where's the most famous example of mercury in literature? So who said that? Who said it? What is it? Hatters. Yes, Mad Hatter in Alice in Wonderland, right? They used to use mercury to make their top hat stiff, and it makes you mad, sends you crazy, and hence the Mad Hatter. So we don't use mercury quite so much anymore. It used to be using fillings in your teeth. Bad idea. We've learned from our bad ideas, and mercury now is avoided if you possibly can. But this is such a good method that it's still used. You can see here what's happening is an addition, where the alkene is picking up an OH group from someplace, and it's picking up mercury. Now, mercury is going to be one of the first metals we've seen used, and as a reagent, it's going to be electrophilic, which is kind of interesting. And then you don't want the mercury in there. You want to get rid of the mercury, so we'll do a second step called demercuration, just get rid of the mercury, and you end up with a hydroxyl group. And look what happened. The OH group ended up on what we might call the Markovnikov position. It ended up at the secondary position, not the primary position. So the mechanism for this will be a little bit different because it doesn't involve carbocations rearranging, so probably it doesn't involve carbocations per se, and we've got to be careful here. So if we think about what we've done mechanistically, so far we have challenged an alkene with a positive thing, and that alkene has gone after that positive thing, so far a proton, and added and given us an intermediate species. So you should be comfortable by now, having read the first part of this chapter, and I will put the chapter 9 homework up tonight, tomorrow when I get round to it. You can see here protonation of that pi bond gives a tertiary carbocation. That's what we've dealt with so far. Well, if you choose to use mercury, and this mercury salt is going to be such that it gives you a mercury electrophile, and that mercury electrophile serves two species, right? It's a really interesting piece because now it's a positive charge, so it's like a proton. But it also has this, right? And this is key. Not a little smiley face, but a lone pair. Okay? That lone pair is key. So this guy has a proton type reactivity, and it has a nucleophile type reactivity, because it has both positive charge and lone pair. So what it can do is it can add to the pi bond, and it can add to both carbons. And that's the key here. So when you draw these types of pictures, that usually isn't thought to be significant, because that looks like a carbocation. And if this thing is known not to rearrange, it probably isn't a carbocation. So this sort of picture here, which are loosely written as resonance structures, this picture here explains our reactivity, explains the fact that we have a very positive electrophilic carbon, but it doesn't rearrange because it's not a full carbocation. If it's not a full carbocation and it's simply delta plus, it'll do the same chemistry as if it were a carbocation, but it won't rearrange. So with that in mind, the sort of accepted mechanism is as follows. You're going to add the one piece, but like so, and you're going to add the second bond like that. That's the mechanism I like. The first arrow is from the pi bond to the mercury. The second arrow is from the mercury lone pair back to the carbon that's losing out. And what that will give you is this mercurium ion. It's the first example we have seen of a three-membered intermediate. And we're going to see at the end of this chapter, the author summarizes this by trying to bring all the common features together so that you're not learning this thing three times. These small three-membered rings. What do you know about three-membered rings? They are strained, so they tend not to last. Or if they do last in the second semester, we'll use them as reactive species. But in this case, this is not going to last. It's a mercury, which is quite a large atom, in a small three-membered ring. This will be an intermediate, but it's not a full carbocation like we've seen. Now, to understand this species, we have to be on our toes, because it looks like the mercury is positive. And if you go to these pictures, yes, the mercury has some positive charge. But if this molecule is trying to break apart or break open, one of those bonds has to break, right? Now, the carbon-carbon bonds really can't break. There's no pathway for that here. But this can break, where the mercury is trying to get its lone pair back. And if that's the case, this bond elongates. And I'm going to elongate that bond in what looks like a transition state and put some delta positive on mercury and put some delta positive on carbon. Now, the regioselectivity here, why the nucleophile attacks the tertiary carbon, should be fairly apparent. Would you rather have positive charge developing here on the left or developing here on the right? Left, why? More substituted, absolutely. It's tertiary, it's more substituted. That carbon should be able to handle that easier. Now, this is the first of three examples we'll see with this type of idea. Be comfortable with it. That's a pretty strained ring. It wants to open up. If it wants to open up, it means, you take your model kit, it pops open. This will want to pop open in this manner so that mercury gets its lone pair back, and that results in one of the carbons becoming more positive than the other. And you want to have the tertiary carbon more positive than the secondary because it's just better at handling that. But if you look at that picture, I don't see a full carbocation. If you're happy with transition state, delta positives, delta negatives, this should be fairly straightforward, right? You are sharing that positive charge between two atoms, which we've seen before, and you are thinking now about this guy here being more positive. So what happens next is the nucleophile comes in. The nucleophile in this case is water, H2O, because that's the product we're trying to get to. Well, all right. I've been yabbering on at you for 9 weeks now about tertiary systems being crowded. All of a sudden, my nucleophile is attacking a crowded tertiary carbon. Why is that allowed? Think about geometry. Think about the change in this. If it was sp3 hybridized, it would be too big, right? Everything would be in the way and we wouldn't be able to attack. What is happening to that carbon if it's starting to develop a positive charge? What shape is it becoming? Trigonal planar, right? So it's not really sp3, it's somewhere in between. So it's not as bad as it looks. And the nucleophile is now attacking the carbon that needs the help. It's attacking the carbon that has the most positive charge, which in this case is tertiary. Now that's counterintuitive from where we've been so far, but you have to be on your toes here. It isn't really sp3 anymore, this carbon here. It is becoming sp2. And if it's becoming sp2, all those groups that were getting in the way in the SN1 reaction are getting out of the way, so the nucleophile can approach. Go ahead. So the mercury attaches from one face, and there's a long discussion coming up probably on Friday about attacks on different faces, right? We'll save that for Friday, because it's Halloween, yeah, and it's really scary. But we're starting to develop that idea. You are seeing subtleties now. This is not a completely sp3 carbon, because the mercury is pulling its electrons back, away, making this guy positive or slightly positive, and that must result in a change in shape. Is it completely flat like a carbocation? No, because you do have that mercury on top, and it's it's somewhere in between. But we're developing sort of subtleties now to help us explain outcomes. So if we do that, and we add the nucleophile, in our case we're going to add water, we have a very nice process for adding OH to the more crowded carbon in the same way you would for Markovnikov, but it avoids the carbocation. You don't need a carbocation here, and in fact it doesn't happen. And the proof of the fact that there's no carbocation, you don't get any rearrangements. So this is a very nice addition to Markovnikov addition of H2O, using the mercury to be able to put the hydroxyl where you want it to go. You are guiding the hydroxyl to the place you want it. Now, this second step, we need to get rid of this mercury, and we need to replace it with an H, right? You think about what we add in the Markovnikov addition, we add H2O. So our second H must go in somehow. And I'm going to put an asterisk here. I don't like doing this, but I think it's necessary at this stage because the mechanism is not very well understood. So I'm not going to have you worry about it just yet. But what happens here is the mercury is replaced by one of these hydrogens. We will spend quite a bit of time with this guy on in chapter 14, I think it is, next term. You will see that in great detail. But right now, this replaces the mercury, and it gives you that CH bond. And what you've done overall now is you've placed the OH group at the more crowded carbon, you place the H at the less crowded carbon, you've got your Markovnikov addition product without having to worry about carbocations. That's very useful. Okay, chapter 9 is all about, if the engineer is looking for ways to solve problems, these are ways to solve problems. These are really useful reactions that allow you to do things that otherwise might be tricky. People say something because I'm about to ask questions. I mean, I've got 25 minutes, 25 American minutes, 60 seconds each. Hello, Dodson, what's up? So if you think about it, it turns out this is nucleophilic, right? As you'll see next term, it's actually a nucleophile, which is electron rich. And if you put a hydroxyl here, it's also electron rich, so they should repel. Yeah? It will all make horrible sense. There'll be some point over winter break, you'll be sat there, I don't know, or shoveling snow or whatever, and you'll sit there and go, wow. Wow. Because it all makes sense for most of you. Go on. We are trying to avoid carbocations. That's the whole point of this reaction, is to avoid carbocations, because carbocations can rearrange. You don't want that. So this is a nice, added sort of feature that was developed to avoid those issues. Okay? What you'll see between now and the end of this semester, which isn't that far away if you think about what's coming up, we have Veterans Day coming up, we have Thanksgiving coming up, and then boom, finals week. Yeah, it's going to get very busy. November is on Sunday, right? It's getting very busy soon. So be careful here. Keep up with this stuff. Make sure you're answering questions along the way so that we can do well. Well, I'm procrastinating because we're about to do this. And this was voted one of the 2 least loved mechanisms in the entire 2-semester class. The other one's coming up on Friday. Least loved, yes? Not liked much at all, unless you're a chemist. Well, what we're trying to develop here is a game, is what we do for a living. You know, we haven't really talked about what I do yet, which is organic synthesis and make molecules and design multi-step syntheses to make a product that might have some use. And we need a toolkit. We need a collection of reactions that will allow us to do what we want it to do. So if you are thinking about, you know, I don't know what hobbies people have, but I do woodwork. I make things out of wood. So in my garage, much to my wife's annoyance, I have 5 different saws. Because if I'm trying to cut a piece of wood with the wrong saw, I'll kill myself. Right? I have the right tool to do the right job. Organic chemists have the same thing, right? Have the same idea. We need the right tools to do the right job, or else it's not going to work for us. It could be dangerous, or it certainly is going to be uneconomical. And the engineers will have an interest here because, you know, most of your jobs will be on scale. My lab, most of the reactions I do, I mean, I just this morning dried a 250 ml flask. A 250 ml flask is about the size of my fist. That's about as big as it gets for me. For the engineers, your flasks are about the size of this building. Okay, so you've got all these different pressures. You know, why do you do thermo and transport and all that stuff? Because these chemicals have got these properties that you have to be aware of as you build on bigger scale. So this toolkit is going someplace. You look at what we've done in Chapter 8, and this is the organization I asked you to do, and can do this in office hours quite easily. Think about what we've done. We've done jobs. We've put OH groups in a certain place. We've put BR in a certain place. We then offered an example of how to put BR in a different place. Because very soon here, certainly in Chapter 12 as we wrap up, we'll be building molecules. On the final, there's always a 20-point question, make this stuff. You've got a lab, you've got goggles, you've got whatever you want, you know, go do it. Make a molecule from everything you've learned this term. And it's fun if you get it, it's not if you don't. So the last of the tools in this sort of 4-tool section of the book is the addition of H2O in the opposite direction. Put it in context. We added HBr to an alkene, it went Markovnikov. It went to the more substituted carbon. If you wanted to switch that outcome and you wanted the bromine to go to the less substituted, you put in some peroxides. You don't know why that works, but you know it does work. That's switched the regiochemistry. What we're going to do now is do the opposite of what we did with the mercuration and with the Markovnikov addition of water using acid. So this is a total change in mechanism. We're going to try and get now the anti-Markovnikov addition of H2O. And this is really challenging. Okay? This is a great mechanism if you like chemistry. It's not if you don't. The argument here is that maybe in my synthesis of some drug or some very useful material, I need a lot of this stuff. And it doesn't exist in nature, let's say. I don't have a source of this that I can get cheaply and easily. So I have to make it. I have to synthesize it. And we need a method that doesn't put my hydroxyl here. Because if I did acid and H2O in this example, my OH group would go there because that would give you the better carbocation. That's the Markovnikov process. Well, this is chemistry from the Big Ten. This is H.C. Brown at, there he is. What a nice man. H.C. Brown at Purdue. And they've got, they're well known in the Big Ten as having 2 Nobel Prize winners in their chemistry department. He developed this chemistry called boration. It's the first use of boron, really, that we have to talk about in detail. So we're going to add a boron reagent. It's going to be electrophilic. It wants electrons, so it reacts with the pi bond. And we're going to react in a second step with peroxide and sodium hydroxide, and that's where the hydroxyl comes from. This is a very, very tricky mechanism. It takes me, I mean, it'll take me the rest of today to do it. We're getting anti-Markovnikov outcome here. So can this be through a carbocation? Think about the logic of this stuff. Can it be through a carbocation if I'm getting the opposite isomer to what I got earlier? No, it can't. So first thing you do here is no carbocations. You think about the third exam, the final coming up, you have to make some pretty quick decisions. Is it a carbocation? Yes, it might rearrange. Is it a carbocation? No. What else is going to happen? And so far we've done stepwise processes. Now we're going to do, in this reaction, a concerted process. So the mechanism will change fundamentally. This cannot be a stepwise carbocation formation, or else you'd get the opposite product. So, you know, what type of chemistry gives you Nobel Prizes? Very useful chemistry. Stuff like this, which is used on huge scale. It's safe, it's very general, brilliant stuff. And it gives you what you want. So, when I was in school, wow, last century, wow, we learned this one. And this to me is like quant. How's quant, Joe? Enjoying it? I didn't hear you say that. I didn't hear that. Look at that equation at the bottom, or those 2 equations at the bottom. This is going back to general chemistry. If you have flashbacks, I apologize. Okay? In the first step, if you use BH3, borane, right? So borane is B with 3 hydrogens attached. It's kind of fun because it's like aluminium, It's missing a bond. Carbon has 4 bonds. Water's got 2 bonds and 2 lone pairs, but this guy's only got 6 electrons. It's happy like that, but it will react with other things that are nucleophilic. So this will be a Lewis acid. This is maybe the first example of a non-protic acid that we're about to use, Lewis acid. It does the same things that protons do. It actually does the same things that carbocations do. It reacts with electron-rich things to form new bonds, and this is incredibly useful. So the stoichiometry down here is kind of nasty. You buy BH3 as B2H6, diborane. And diborane breaks up in solution to give you BH3. But of course, you've now got 2 molecules of this, and you've got the need to react with 6 molecules of this. Where does that come from? Well, you've got 3 of these hydrogens. We're going to add each of those hydrogens to an alkene. And you've got 3 of them. So down here, you've got 6 of them. That's why you need 6 alkenes. You add those 6 alkenes to the 1 molecule of B2H6, which is really BH3, you end up with a borane. So I'm trying to use the language here so we can do this carefully. Borane, B-O-A, not boring, but borane. They're different. And that guy now is the product of that first step. We have added BH bonds to an alkene to give us a saturated product. And that then is 2 molecules of that are formed, and it's trivalent, and all of a sudden it's like, wow. And then we take a second step, and we take this borane from that reaction, and we treat it with sodium hydroxide and peroxide. But we need, for every molecule of this, we need a lot of this, and we need 3 molecules of peroxide. And that gives me 3 molecules of this and a molecule of sodium borate overall. That's just too much. Okay? So we're not going to worry about that. You're going to look at that if you're taking a standardized test. If any of you have to take an MCAT, GRE, IRS, whatever you have to do in the future, you have to think about this. They usually use the simple example. We choose to use a more relevant, more modern, a better example than this, which is also simpler, more simple to learn. So don't worry about that stoichiometry, because we're going to use this guy. Not the guy at the bottom, but the guy at the top. One of Brown's major accomplishments was realizing that you could take borane, BH3, and add it to alkenes and make these types of things. Now, do you have to be able to draw that thing? No. You have to be able to draw it like this, because we have all these abbreviations. And the reason it's called a parachute is because if you turn your head like that, it looks like, don't do it. It looks like a parachute. Or you're under a parachute and it got windy, and you're in trouble. Do you see a parachute? I see a parachute, right? So all of this stuff is abbreviated to this. The way this reaction works is fairly simple. BH bond is reactive. The B is electrophilic. It likes electrons. It's going to go after the pi bond. And we're going to add this stuff in a sort of a certain way so that we get the less substituted alkene at the end. We get the primary alkene instead of the secondary, or the secondary instead of the tertiary. So if I asked you to, if I do this, and then I do this, what am I suggesting? Large. The little hydrogen on the right is small, all right? And the big thing with the boron on the right is large. That's all there is to it. You recognize that? This is great stuff. There's not a lot to this reaction, because all we're going to do now is change the mechanism fundamentally by not talking about carbocations, but talking about steric environment. Talking about large pieces, want to avoid large pieces, if you possibly can. So we will now deal with this. I will teach you this one because I think it's more modern. It works better. You get better yields and better selectivities. And guess what? You only have 1 hydrogen. So you only have to do this once. On the previous slide, we had 6 hydrogens. It got very complicated. Now we have 1 hydrogen. I like that. So once we've got the idea of what the reagent looks like, the parachute borane, we can now start to use it. Mechanistically, it's all about the boron wanting electrons. In fact, boron is used as sort of a mimic of carbocations because it has very similar properties. It's missing the 4th valence. The carbocation is positive, the boron is neutral, but they are both the same structure. They are both trigonal planar. They both have an empty p orbital that could be attacked. So the whole point of this is that if you have some nucleophile, like a pi bond, it will go after that boron, just like it went after a proton. So if you're okay with protons, you should be okay with boron. They both need electrons. The pi bond can serve as that source of electrons. So, boron, in the shape of parachute borane, this molecule that is small at one end, large at the other end, is going to interact with an alkene. And all of a sudden we can start talking about transition states, stereochemistry, how things happen, and get this out of the way now. In this experiment at the top, there's more to this coming up, and there's a great explanation. I might not get all of this done today, but that's okay. That alkene is what shape, roughly? Trigonal planar, flat around the alkene. So if I have some reagent approaching it, what are the chances of attack at one side versus the other? About the same, equal, right? Unless there's something else in the molecule that's changing things where there isn't here, you should attack from both sides. So here's a fact. Here's the experiment and here's the outcome. In this reaction, in the first step, you put the boron here. In the first step, you put the boron there. That first step only gives you two outcomes. Why should that make a difference? Well, look at the possibilities here. I now have this with 4 different things attached, and I have that with 4 different things attached. Okay? So I have 2 chiral centers. I've introduced 2 chiral centers by doing this addition reaction. If I have 2 chiral centers, how many isomers are potentially possible? 4. I only get 2 of them. This is the beginning, and I'll point this out, the stereochemical sort of the worksheet that I have people think about before the end of term. If you can handle that, you can handle a second semester. The stereochemical outcome here informs you about the mechanism, because you only get 2 products. And look at the orientation of those products. If I asked you to give me a word that describes the relationship between that BH and that H, what is it? They're eclipsed, right? They're syn. They're on the same side of the molecule. Likewise over here, this is a dash, this is a dash. They're on the same side of the molecule. What is the difference down at the bottom? I am not getting these products. They are not forming. So I'm not getting dash wedge, wedge dash. Those guys just don't happen in this reaction, it's a fact. So where do they go? They don't form. If you only get those 2 products at the top, that tells you a lot about that process. Okay? Do this carefully. If this was a carbocation driven process, and I have a flat carbocation, what are my chances of attack from both sides? 50-50, right? And I've got an alkene which is flat. And what are my chances of attack from that? 50-50. If I have 2 stereocenters, and it's a completely sort of carbocation driven process, I should get up, up, down, down, up, down, down, up. I should get them all, if indeed we're dealing with carbocations, because you can attack from any side. You should get them all, but you don't. So that's very useful information for you as a scientist, because you can now say the mechanism does not involve carbocations, because if it did, I'd get 4 products. So where are the other 2? They don't form, no carbocation. So what's the other possibility? Carbocation was a stepwise process. What's the other big possibility? Concerted. So all of this is both pieces, the B and the H, adding at the same time. That B and that H will add to one face at the same time like that to give maybe 2 wedges, and it'll add from this face in a different molecule at the same time to give you 2 dashes, which is where those top two products come from. So there's the proof of the fact that this is concerted. The 2 products here both have the B and the H in the same direction, therefore everything must have happened at once. There's not enough material. You think about a BH bond, that's not very long. You can't add the H at one side and then try and add the B underneath. There's not enough material to do that. So this is the proof that it adds at the same time. So this is a concerted process that is said to be both stereoselective and regioselective. Stereoselective is fairly obvious. We're getting addition at the top and the bottom, but not both. And the regioselective will come up in a second when we look at the actual process. So we're building an argument here for why this is happening. It's not just a fact now, we're actually trying to prove it. Here we go. In the first step, the addition of what we're calling now the parachute borane goes in such a way that both pieces, both components, the B and the H, add to the same face. So I get in this system 2 dashes. In the second step, this mixture, sodium hydroxide and peroxide, seems to replace the B with an OH. So I've got several issues here of stereochemistry. The syn addition, as we'll call it, results in the stereochemistry as shown, and then something else is happening in that final product. Is this an inversion? No. Is it a racemization? Am I getting a mixture? Not from what I can see on that slide. So what's the word for that if you don't change stereochemistry? It's retained, retention. Retention of stereochemistry. That's a big clue again as to what happened in the mechanism. So that second step, which will be Friday, which is perfect, isn't it, because it's Halloween. Yeah? Friday's going to be great. Dress up, have fun. Be awake, Santaganters, whatever you can do. Come dressed as each other, whatever you want to do, you know, exactly. In this situation, we've now got to worry about that retention and how we got there. Because, get this, in that second step, which we haven't seen yet, if I get the same stereochemistry, that's going to suggest a rearrangement, a concerted rearrangement. It's going to tell you it's not a carbocation. Because guess, if this guy here breaks off, and I form a carbocation, All right, my boron broke off from down here, and I make a carbocation. Where can my next piece add from? Either side, and I get a wedge and a dash. I don't. So that tells you no carbocation. So mechanistically, we've got to worry about regiochemistry. We've got to worry about the arrows that you push, the transition states that you draw, the size of the pieces, and how that affects the outcome. We have two possibilities here. What I've got at the bottom is a biased alkene. I've got this guy, right, 2-methylpropene. The alkene is basically serving as a nucleophile going after the boron, and the hydrogen is attaching like so. That would be the set of arrows that you use to describe that process. Nucleophilic double bond goes to the electrophilic boron, and the hydrogen goes back to replace, to make everything neutral. Joe? It's not a proton transfer at all. It actually looks like it's a hydride. In this example, the H looks like it's behaving as a nucleophile. Don't even go there, right? You could actually say that, to be fair, yeah. I mean, you could argue that the first arrow that I drew there was a proton transfer in the sense that boron acts like a proton. But you could also call it nucleophilic attack, yes, followed by replacement. Now, down here, finishing this up and then thinking about Friday and the second step. If I drew this molecule, which is the precursor for these two transition states, I've got two hydrogens at one end, I've got two methyl groups at the other end, carbon here and carbon here. Which of these two alkene carbons is easier to get to? The left or the right? The one on the right, everybody can see that, yeah? The one with the hydrogens is easier to get to. So I've got this large boron piece looking at this molecule, trying to decide which way it wants to orientate itself to do the addition. So does it make sense that the large group from the boron avoids the methyl groups? That's all there is to it. There's your regioselectivity. That massive parachute bicyclic structure is very large. It wants to avoid all the steric stuff on the alkene. So it's going to avoid the large end. So we're going to see two possible orientations, how this works in terms of regioselectivity. We're going to see one possibility where the two add like so to avoid each other, and another possibility in a second where they don't. Now, what this tells you at the top is that this is not a carbocation, this is a concerted process. And I want you to spend some time having a look at that, because that's a tricky transition state. That looks like a four-membered transition state. Four-membered ring. Everything's happening at once. The alkene is bonding to the boron-hydrogen bond is breaking, the hydrogen is bonding to the carbon over here, and the alkene is breaking itself. That's a pretty difficult transition state. We'll deal with more detail on that on Friday. So far what we've done is said that this is sort of similar to a proton adding, and we're now going to get stereochemical issues because of the fact that everything's happening at once. Both pieces are happening at once. Everything we've done so far, we added one thing, then something else came in. Now everything's happening at once. So here we go. Here are my two transition states to try and show you the regioselectivity. The stereoselectivity is basically, it adds from the one face and it adds from the other face, not both at the same time. Here's my picture to show one transition state. Here's my picture to show the second transition state. On the right-hand side, if this is this big parachute thing, there's your problem right there. This and this are going to bang into these two things, and that's bad. Okay? That's not good. On the left, little hydrogen has no problem whatsoever getting there, because there's no problem up there, and these big groups are out of the way. That is good. I can't do this, can I? There we go. Hey. Okay. That symbol is actually accepted these days in organic chemistry because it's fast to draw. Right? That's a good thing. So here we go. Here we go. We've got regioselectivity, we've got stereoselectivity. I've got a couple of minutes left, and I want to show you where we're going on Friday. We now have a method based on a different mechanism that will put the hydroxyl group where you want it to go. It will go to the less crowded carbon. The word crowded now is operative because we're talking about steric environments. We've got a system here now which has two different carbons in the double bond. If you add this, which is our parachute, you put the boron here and the hydrogen here. Then, somehow, and this is kind of Harry Potter, this second sort of witch's brew gives you the hydroxyl in that place. And that mechanism is fantastic. And it does it in a concerted process. What we've learned today, the boron and the hydrogen add at the same time. Electron pair from the alkene goes to the boron goes to the less crowded carbon, hydrogen goes that direction to add to the other carbon. I have a new bond. I have a new system in which my boron now is added, and they both added to the same face. We described that as syn addition. Joe?
What happens to the
That's, if I want to be careful here, I probably should do that. Make more sense? Yeah, it's one of those subjects, we're getting into the subject now where those little differences of maybe 0.5 millimeter in an arrow makes a difference. So I get a syn addition. I want to warn you about Friday. We're going to do this. And this is an hello? Bye-bye. Second step is oxidation. Second step is the start of Friday. We take peroxide and we take hydroxide, we deprotonate one and we get this. And this peroxide is a nucleophile. It goes after the boron because boron is still 3-valent. We then get a rearrangement. We then get rearrangement from boron to oxygen. Different. And we end up with an OB bond, which then gets hydrolyzed. That is problematic. That is always an issue. So do some reading before Friday, and let's see what we can do then.
So whenever we see this,
Give me a minute, Brandon.